So, welcome to our lecture series on advanced linear algebra. In my last class, we have shown for every n cross n square invertible matrix, there exists unique lower triangular matrix with entries on the main diagonals are positive and also a unitary matrix such that the unitary matrix equal to lower triangular matrix multiplied to the your given invertible matrix. So, now let me consider on examples, so that how to obtain the lower triangular matrix, that will be clear. So, let me consider, let x1 square plus x2 square equal to 1 with x1 is strictly greater than 0. So, consider an invertible matrix, say capital A equal to like this x1, x2, 0, 0, 1, 0, 0, 0, 1. So, that I am confirmed the given matrix is invertible. We want to find a lower triangular matrix, say capital M, such that M into A equal to some unitary matrix, a unitary matrix. How to find the lower triangular matrix? So, I have to follow the proof how the matrix M has been constructed. So, let me go to the Gram-Schmidt orthogonal procedures. Let the rows of A by say beta 1, beta 2 and beta 3, that is beta 1 equal to, I have considered x1, x2, 0, beta 2 equal to 0, 1, 0, beta 3 equal to 0, 0, 1. Using Gram-Schmidt orthogonalization procedure, consider beta 1 equal to as alpha 1 and alpha 2 equal to beta 2 minus inner product of beta 2 and alpha 1 by norm of alpha 1 square into alpha 1. So, this is equal to, so this will be equal to beta 2 equal to 0, 1, 0 minus beta 2 and alpha 1. So, it will be straight away I can take dot product, alpha 1 is equal to beta 1. So, it will be x 2 into alpha 1, fine. So, this can be rewritten, this implies alpha 2 equal to 0, 1, 0 minus x 2 by, see alpha 1 is equal to x 1, x 2, 0. So, alpha 1 square is equal to x 1 square plus x 2 square, which is equal to 1. So, norm of alpha 1 square will be equal to this one. So, this implies that it will be 1 into your x 1, x 2 0. Okay. This can be written straight away minus x2 x1 1 minus x2 square 0, and this is also equal to, I can write down 0 1 0 minus x2 into beta 1, because I need to express in terms of beta 1 also. So, this is beta 2 minus x2 into beta 1. So, alpha 2 equal to this quantity, fine. Alpha 3 is equal to beta 3 minus beta 3 alpha 1 by norm of alpha 1 square into alpha 1 minus beta 3 alpha 2 by norm of alpha 2 square and alpha 2. Now, this is equal to beta 3 means 0 0 1, and inner product of beta 3 and alpha 1, that is equal to 0, because alpha 1 contain first and second entry and beta 3 contain only non-zero at the third entry. So, therefore, it has to be 0. So, minus 0, and similarly beta 3, inner product of beta 3 and eta alpha 2 will be also 0. So, this implies u is equal to, which is equal to your alpha 1 by norm of alpha 1, alpha 2 by norm of alpha 2, and alpha 3 divided by norm of alpha 3. This is the U matrix. We know that unitary matrix U will be equal to the orthonormal vectors, that is alpha 1 by norm of alpha 1, alpha 2 by norm of alpha 2, alpha 3 by norm of alpha 3. So, this equal to something m into capital A. So, what is our capital M? Here we have capital M will be equal to, according to the definitions what we have already learned in our last lectures. So, the coefficient, that is, if you recall, we know mkj equal to minus ck j divided by alpha k when j less than k, and it is equal to 1 by norm of alpha k when j equal to k and 0, for j greater than k it is 0. So, according to that definition, so we have already obtained what is ckj. See, for first row it will be then certainly 1 0 0. Second row of m will be, that is your C2j minus C2j, I am getting here alpha 2 minus x2. So, it will be x2, and then this one will be equal to 1. By the way, I have to also find out the norm of alpha 2. Norm of alpha 2 will be equal to how much? Norm of alpha 2 square will be equal to x2 x1 square plus 1 minus x2 square whole square. But 1 minus x2 square is equal to, according to this is x1 square. This is equal to x2 square x1 square plus x1 to the power 4. So, this is equal to x1 square into x2 square plus x1 square. This is equal to x1 square. So, norm of alpha 2 is equal to x1. So, this means that I have to take a norm of alpha 2. So, x2 by x1 will be there, and this will be also 1 by x1. Okay. So, minus will be there, yeah, minus x2 by x1 1 by x1 and 0. The last one will be what? 0, 0, 1, because norm of alpha 3 equal to 1. So, this is capital M. This implies I will have alpha 1 by norm of alpha 1 x1, x2, 0, first row of capital U, second row of capital U will be alpha 2, this divided by norm of alpha 2, norm of alpha 2 is equal to x1. So, it will be minus x2 and then 1 minus x2 square means x1 square. So, this will be simply x1 and this will be 0, and third one will be 0, 0, 1. This will be equal to 1, 0, 0 minus x2 by x1, 1 by x1, 0, 0, 0, 1 into your original matrix, that is x1, x2, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. You can cross check whether this calculation is correct or not, and but the procedure is like this. So, in this way you can find out a lower triangular matrix for any given n cross n invertible complex matrix. Okay, so now we will turn to this some another interesting fact by raising a questions. The question is like this: if T be a linear operator on a finite dimensional inner product space, then under what condition inner product space a capital V, then under what condition the space V will have an orthonormal basis, which are eigenvector of the operator T. So, let me raise this questions that if we picked up any linear operator on a finite dimensional inner product space, say capital V, then under what condition the space V will have an orthonormal basis, which are basically eigenvectors of the given operator. Now, to answer these questions, I will first consider, suppose a linear operator T is defined on a finite dimensional inner product space and the space has an orthonormal basis, which are basically eigenvectors of the operator T, then what sort of characteristics of the operator one can find it. So, let me cross check that one first, so that will give a hint to answer these questions. So, to answer these questions, I will first consider the case when T is a linear operator on finite dimensional inner product space V and V has an orthonormal basis consists of eigenvectors of T. So, I have taken reverse way. Suppose the operator T is defined on an inner product space and the space has an orthonormal basis consisting of the eigenvectors of the T, then I want to know what is the typical characteristic one may see on this operator. Maybe that will give a hint to answer the above questions. So, I have taken an operator T which is defined over a finite dimensional vector space inner product space V. So, let B equal to alpha 1, alpha 2, alpha n be an orthonormal basis for capital V with T of alpha I equal to C I alpha I, where C I belongs to the corresponding field F, that is field on which the space V is defined. Okay. So, I mean to say here C I is basically eigenvalue of the operator T and I equal to 1 to n. So, this implies the matrix representation of T with respect to this given order basis B will be of the form of a diagonal matrix like C1, C2 and Cn, like this. The matrix representation will be like this. Now, the question is, what about the adjoint of T with respect to same order? Since V is finite dimensional, so operator T will certainly have adjoint. The matrix representation of T star with respect to B will be also a diagonal matrix with diagonal entries as C1 bar, C2 bar and Cn bar. If the inner product space is defined over real Ci bar equal to Ci. So, in that case the matrix representation of T with respect to B will be equal to matrix representation of T star with respect to B, and this implies that you will have T equal to T star, T equal to T star. This implies the operator T will be a self adjoint operator. But if eigenvalues are complex, then or if the eigenvalues are complex, or if the matrix is defined over the complex, I mean inner product space is defined over the complex field. So, in that case T may not be equal to T star, T may not be equal to T star, but since a matrix representation of T and matrix representation of T star both are diagonal matrix, so product of diagonal matrix will be again diagonal matrix. So, in that case this implies that you will have T into T star equal to T star into T. So, now we have seen when a linear operator defined on a finite dimensional inner product space and the space has a orthonormal basis consisting of eigenvector of the operator, then there are two situations when the eigenvalues are basically real. Then in that case I am getting that the operator is self adjoint operator because T star equal to T. But if it is eigenvalues are not real, in that case I am not saying that T star will be equal to T, but certainly I will have T into T star equal to T star into T. Now this will give a hint, and this is a very fantastic hint, that it is also sufficient condition if the operator T satisfying this condition, then certainly will have a orthonormal basis of the space consisting of the eigenvector of the operator T. I will give the proof later on, we are going to prove that part later, but before going to the proof of that part, let me introduce a nice operator called a normal operator. Let T be a linear operator on a finite dimensional inner product space V. T is said to be normal if T into T star equal to T star into T. One may have a question in the mind while defining normal operator in this way, have taken that the operator defined over a finite dimensional space. Why it is, why we have restricted to the finite dimensional inner product space? The reason is, if you consider finite dimensional inner product space, existence of the adjoint is guaranteed. So based on that only I am defining here that a linear operator T on a finite dimensional inner product space will be normal if T into T star, when T, the operator T and the adjoint commutes each other. That is, T commutes with its adjoint. See, as a special case, if T is a self adjoint, then also we have T into T star equal to T star into T. Self adjoint means T equal to T star. So T into T star is equal to T square. So this property holds good. So this implies that every self adjoint operator is normal operator. What about unitary operator? We have for unitary operator U into U star is equal to U star into U equal to identity. So this implies here also U commutes with adjoint, U is also normal operator. So every unitary operator is also normal operator, every self adjoint operator is also normal operator. Before going to answer the question which I raised at the very beginning, I will first try to answer the questions related to the special case, that is self adjoint operator. So let me say what is the characteristic of the self adjoint operator. This is a small theorem, it is like this. let T be a self adjoint operator on a inner product space say capital V. Then the eigenvalues of T are real. Second, the eigenvectors associated to different eigenvalues are orthogonal, Let me prove these results. Let C be an eigenvalue of T. So, this implies there exists 0 not equal to alpha belongs to this V, T alpha equal to C alpha. So, this implies C into inner product of alpha alpha, this is equal to, I can write down C alpha alpha, which is equal to inner product of T alpha alpha. Okay. So, this is equal to again alpha T star alpha. So, this implies inner product of C alpha alpha, which is equal to inner product of alpha T alpha, because self adjoint means since T equal to T star. So, this is equal to inner product of alpha and C alpha, which is equal to C bar alpha alpha. Since alpha non-zero, so this implies that I will have C minus C bar into inner product of alpha alpha equal to 0. Since inner product of alpha alpha not equal to 0 implies C minus C bar equal to 0 implies C equal to C bar. So, this implies C is real. Let beta belongs to V be another vector such that T of beta equal to D times beta and D not equal to C, D not equal to C. So, this implies inner product of C alpha alpha, which is equal to T alpha alpha, which is equal to alpha T star alpha. Let me consider beta, T star beta. So, this is equal to inner product of alpha and T star beta equal to T beta. So, T beta equal to D beta, which is equal to D bar alpha beta, but we know D bar also D because all eigenvalues are real. So, this implies C into inner product of alpha beta equal to D times inner product of alpha beta. So, this implies C minus D times inner product of alpha beta equal to 0. Since C minus D not equal to 0 implies alpha beta equal to 0. This shows that alpha is orthogonal to beta. So, for different eigenvector associated to different eigenvalues are orthogonal to each other. We will continue more about it in our next class.